Welcome back, guys. I think we have stopped up to this in our last video. So I asked you guys to calculate the length of this slip gauge. So x1, x2 is their original position, final position. So x2 minus x1 is 137.44 minus 68.93. This difference. Then you have to subtract this probe diameter also because compensation you have to do. So after doing that, I hope you will be getting 65.51 millimeter is the length of this bar. Maybe we can say it's a gauge. Okay, I hope you got that too. Okay, so this video will be checking about calibration. So before why we want to do the calibration, we want to ensure whether is there error or not. So definitely error possibilities are more. Various reasons for error also there. So some of the error reasons it is given here. Basically wear and tear or continuous usage, or if we are doing some shifting or environmental error. Okay, so like that only it will come. It will create some errors. In terms of industry, they will be mostly keeping the CMM inside a controlled environment. In our lab also you might have witnessed, but many people are moving here and there and coming, opening, closing door, and machines are running in another room, like CNC machines or milling machines, kind of conventional machines also running. So all this vibration will affect the positioning errors or accuracy of measurements. So you need to do always you need to do some error calculation or calibration you have to do. That's what always I used to say. Any activity you guys are going to do for your project, any instruments you guys are going to do, or you are buying some instruments for your a project, or you are designing any instruments for your own project, you have to do the calibration, and you have to identify the uncertainty of that particular instrument which you are going to use it for your experiment or your project. Okay, so uncertainty calculation is very much important. So uncertainty calculation in the sense calibration will come. Okay, so that what so calibration are needed in the sense possibilities of error is first important. As I said, the table and probes are in imperfect alignment. If table and probe are there, if it is not aligned properly, you will be getting error. The probes may have a degrees of run out and move up and down in z-axis. That may occur perpendicularity error. So if table move up and down in terms of x-axis, or some probes having some run out error, then perpendicularity error may occur. So CMM must be always calibrated by using master plates before using the machine. If you want to use CMM machine for any measurement purpose or inspection or scanning purpose, we must do calibration. So that is what you also witnessed during your visit in our lab. Okay. Then straightness and perpendicularity of the gateways. So all will leads to dimensional error. Okay, dimensional errors of CMM, which are influenced by these reasons: straightness and perpendicularity of the gateways. So if straightness and perpendicular of the gateways goes wrong, then you will be getting dimensional error. So again, it will lead to how to measure straightness or how to measure the perpendicularity. Maybe you might have studied about second unit and third unit about laser interferometer, interference or interferometry. Okay, that concept we can mostly laser interferometers will be used in terms of measuring CMM. So by keeping multiple reflectors and cameras or what to say lenses, optics and all, they can able to. So straightness and perpendicularity of the gateways needs to be checked. So that could lead, if it is not maintained properly, then lead to error. Then scale deviation and adjustment. If you are doing some measurement calculation error, like computational errors, practical errors also there. We'll discuss about in the coming slide. So due to that, and also probe length is not maintained properly, or probe system is not calibrated. Previously, I said how to do the calibration of the probe. Okay, so like as stated, you have to keep the sphere and at least in four places as per ISO. You have to do the calibration and check the reading. That probing calibration, if not done, you will be getting the error. Okay, then zero setting error, or in software when you are calculating number of digits you are going right, how many number of digits you are considering, and environmental factors like ambient temperature or humidity level and vibration available in and around, our temperature gradients, our thermal coefficient. As I said, it should be very, very minimal. If the thermal coefficient is more with respect to with respect to temperature and time, with respect to time, then deformation may occur. So that may lead to error. So environmental factors also important, which could cause us error in your CMM. Then other causes of errors can be controlled by the manufacturer and minimized by the measuring software. You can able to do some offsetting error or something in some of that say software. They will be providing some zero offset errors. For example, initially if they want to see the values, if it is in home position XYZ position, if it is not that, they can have the control over offsetting error can be minimized by doing some function. There is a function will be there in the software itself. So using that, we can able to avoid that kind of errors. And also, as recommended, length of the probe we have to keep it as minimum as possible so that the deflection error will be avoided. But again, it depends. If your purpose of measurement needs big, like a deep measurement is needed, you can't able to go. So you need, according to the application, but as much as possible, we can keep it small. Weight of work is very, very important. If that table you are going to keep in the granite table of the CMM machine, if it will be having the weight ranges where only that much amount it can carry. If behind which you are constantly loading frequently, then it may have a problem or it may change its geometry or guideways will be there. Since in CMM you might have seen side mounted, top mounted, like different type of guideways are there. So it will affect that weight of the component which you want to measure will affect the table, so that it will affect the gateways, then accuracy of measurement will go wrong. Then variation in the temperature or what are all the humidity factors available will create your errors. Then perpendicularity occurs in three axes. If, as I said, x, y, z, each should have a perpendicular orthogonality. If one goes wrong, every other also, even though it is perpendicular, even though it is maintained properly, other for any one of the axis goes wrong, all measurement goes wrong. So we have to ensure the CMM thing. So that is what causes of errors. So in terms of potential sources of error, in the sense statistical or computational error. So do two in the different sense you have to understand. One is statistical errors can be considered as errors in the measured position of a point on the surface of the workpiece. Errors in the measured position. Okay, that is statistical error. But computational errors, by the word itself, you can understand that errors in the estimated dimensions, okay, and form deviation of the workpiece. So this is during measurement, it's after measurement and while you are doing some calculation. So during measurement, if you are getting some measurement errors, means that is measurement error comes under spatial. Computational errors after measurement, when you are estimating the dimensions from the xyz in the software, if you are encountering like a decimal error or after the digit errors or something like that, then you will be getting the computational errors in detail. What is practical error? The accuracy of component of the CMM, because measurement error where it will come due to the errors in the CMM machine components, errors in the components of the CMM. What are all the things? Gateways, scale, the probe system, or qualifying sphere. Because sphere you will be keeping for inspection and all. If the sphere itself has some errors like a roundness error or positioning error and all is there, means then your measurement error will be there. So guideways. like wear and tear, because it's constantly moving, so wear and tear will be there. Scales are there. It is also goes wrong means measurement accuracy will affect. So it's all measurement errors will comes under practical error. Then, as again I said, environmental factor like ambient temperature, temperature gradient, humidity, vibration will affect, and what kind of probing strategy we are using, the magnitude and direction of the probe force, the type of probe stylus used, and measuring speed of the probe. So because it's going to impact and deflection will be happening. So if and also if we are not properly using the height of the stylus or diameter of the stylus, they are recommending as big as possible. Okay, as big as possible. Sometimes if you are using small diameter of the tip, small diameter of the stylus, but the material of the stylus, if not properly used, then that will also leads to problem. Okay, so that is what that material properties of the stylus also important, and tip, that probe tip, that material also important according to the what kind of material are we going to test. So this all the things you have to keep in mind. Then that also will affect the measurement error and characteristics of the workpiece, like whether the workpiece or component which we are going to inspect, about whether it has elasticity, surface roughness, hardness, mass of the component, all will affect your spectacle error or measurement error. Then computational error, the CMM software used to estimate the geometry of the piece. What kind of software we are using? Whether it's a highly capable of finding out the error and auto fixing, or precision of the computer which we are using. Even though software is good, if it is running, it's not running in good computer. That's why they always recommend some specifications for installing the software, minimum requirement and the number and the relative position of the measured points. Okay, so how many number of readings are we taking, what is the relative position between these points, measured points, also very very important. The extent to which the geometry departs from the ideal geometry form. Okay, that is also important in order to find the computational error. So errors, practical or computational error. So since I said there is a software, inbuilt software will come with each and every software, each and every CMM machine. But initial period it was uh, particular requirement only. Nowadays they are upgrading or outsourcing with some other software and integrating. So what are all the features available in the software means it can measure the dimensional value, dimensional parameters like diameter, center distance, length, or which plane, or whether we can able to connect the data or import the data, or from the coordinate we can able to draw like a CAD diagram, or how we can able to transfer the data or export the data, or can we able to import the data from other CAD software in a different file format like a strip file, STL file format, IGS file format like that. Okay, so depends on that functionality. That software should have the flexibility. Then we can use this kind of software in multiple purpose. Okay, so just for introduction, maybe software in the sense in CMM machine in our robotics lab we have we have our own software, and that software we can able to measure, and we can do the even calibration we can able to perform using that software. We can able to measure the dimensions, length, or we can able to measure the continuous profile, multiple like form features also we can able to measure using that CMM software. It should be more user friendly, then only we can able to easily learn and perform. If it goes again complicated then difficult, so it should be user friendly. Then calibration, since we were discussing about errors in CMM, we need to do the calibration. It is very, very important. What is calibration? Okay, for calibration, basic, it's not about CMM calibration. What is calibration is, you know that very well. It is the process of verifying, it is the process of verifying and adjusting the accuracy. Okay, it is the process of verifying and adjusting the accuracy of the measuring and monitoring equipment. MME in the sense measuring and monitoring. Here, sorry, my profile is hiding here. Measuring and monitoring equipment. MME means measuring and monitoring. It is the process of verifying and adjusting the accuracy of measuring and monitoring equipment and machines by comparing them with the standards of known accuracy. So with the standards of known accuracy, if we measure, monitor, if we verify that and adjusting that with the known standard accuracy, then it is the process called the calibration. The adjustment of instrument is performed by compensating the errors into the instrument. Okay, once we do the verification process, we'll be getting some value. That value needs to be compensated to the instrument so that we can able to get the good readings. The OEM, the original equipment manufacturer of the instrument, usually defines the calibration interval. So when or how often we have to do the calibration, under which environment we have to use this particular instrument. What is the tolerance limit within which the instrument confirm its performance standard? For example, particular CMM means it will be giving like some set of environment or how much accuracy it will give. Everything will be given. So if we follow that procedures only, we could be able to maintain. They also used to give what is the each and every OEM original equipment manufacturer will be giving the procedure to do the calibration, how frequently we have to do. All so we have to certainly follow that kind of procedure. Simply we are buying and keeping in our lab is no. We have to perform regular interval, then only we can able to achieve that accuracy and also repeatability because it's a precision instrument. So accuracy and repeatability also possible if we do the calibration procedure as per the recommendation. And also it needs to be performed in regular interval so as to ensure that instrument is reliable. If we want to rely on the measurement, then we have to do the regular interval. Until otherwise we are not doing any calibration, what are all the measurement we are doing, how we can say it's a reliable? So reliable, how to say it is reliable? By providing uncertainty calculation, uncertainty value of that instrument, then only we can able to claim that that reading which we are taking from that particular instrument, any instrument you take it, it's a reliable. So in terms of CMM, you have to show the uncertainty of the CMM. So when you are doing project in your project presentations or report, you have to give, if you used some instrument, what is the uncertainty of that instrument you have to say. Then only what are the reading you are taking from that particular instrument is reliable. For example, you may be using some vernier caliper or micrometer or height gauges and all in your project, but you are telling accuracy of your vernier height gauge or something you will be telling, but what how you say it's reliable? What is your reliability of that measurement? In the sense, you done calibration of various measuring instruments in our metrology and quality control lab, like measuring various slip gauges like 20 readings or 30 readings and identifying the error, uncertainty errors and all you are calculating, you have to represent that one. That sense you have to develop from the beginning itself. Whenever you are doing some projects, whenever you are using some instrument, you have to ask yourself, what is that reliability of my measurement? How to do, how to prove my data measured from this equipment is right? That calibration you have to do and report it. Then even whether you are presenting in paper presentation or putting in the project report or paper, it is add value to the result you are presenting in that, okay, in that forum. Then importance of calibration. So calibration provides what it will provide us. It will provide us the confidence that their accuracy is as per the given specification of original equipment manufacturer. For example, even though the spec given by that original equipment manufacturer, or you have the pamphlet, it will be given, that pamphlet will be having some accuracy values. Even though it is given, you have to ensure by doing the calibration process, and you are ensuring that it is within the limit of accuracy which they have claimed, that suppliers given. So that will provide you the confidence of your measurement, and also it ensures the repeatability. That is what I said, precision, right? It ensures the repeatability of the measurement taken by the equipment. Okay, you are doing repetitively, you are measuring it, then it will ensure the repeatability. The uncertainty is kept at a minimum level. We should keep the uncertainty level as minimum as possible, further building the confidence of measurement. If, as I said, only 10 readings you are taking, you can able to get some uncertainty value. If you are doing more than 10, 20, 30, 40 readings for calibration, your uncertainty value go down. So it will also boost your confidence for measurement. And calibration through some certified bodies will also increase the confidence of the customer for your organization. For example, instead of testing in our lab itself, if we are doing some projects for the company, in the company, people will be asking whether your equipments are calibrated one or certified one, certified by anyone in the sense. Centralized certification agencies are there, like a National Physical Laboratory, NPLs are there. So they have to certify that instrument. But what are the instruments we have in our labs are not certified by the central agency, but we do the calibration internally, but we need to get some approval. For example, some company people coming and giving projects for their company, and we do. If they are asking, so you are using CNC machines, or you are using CMM machine, or you are using robot, how and how often it is calibrated, where is the calibration certificate, whom certified your instruments, measuring instrument. If you show certificate from a National Physical Laboratory or certified bodies, then that confidence what they will be getting from the company will be getting on our instrument will be higher. So calibration through certified bodies are very very important, and we have to keep the uncertainty level as minimum as possible. It also ensures the repeatability of the measurement, increase the confidence of measurement also. Okay, then in terms of CMM measurement, for CMM there are numerous sources of error. We will be getting numerous sources of error because many components, moving components, some are externally available, some are internally available. So we don't know, if we can't able to detect that, then the usability of the CMM will be uh, question mark. So you have to very very careful in calibrating. Then calibration of CMM is performed. It should be performed according to the ISO. What ISO we have to use? 10360-2. So I will explain what is 10360-2. So I recommend or request you guys to go through at least what is ISO 10360, and also the previous ISO, as I said, ISO 17025. So 17025 is telling general calibration or general testing procedure, but ISO 10360-2 is explaining about calibration of CMM. So NPL has also provided standard procedure for verifying of performance level of CMM by detailed guidelines. So they have their own procedure that also following the ISO only. So they follow the procedure. All these guidelines are provided to perform ER test. What is ER test? We'll discuss in the coming slide. So what is ER test? As I said, remember ER test is the errors and a material standard test. So errors and material standard test only ER test is called. You have to remember that what is in ER test, error and material standard test. This test help in demonstrating traceability to national standard. First unit itself we have discussed what is meant by traceability to national standard. So this ER test will help. So this test help in demonstrating traceability to national standards and estimating the accuracy of the measurements made with the three-dimensional CMM for maintaining confidence and reliability in the measurement. Okay, so in order to maintain the confidence and reliability in the measurements, you have to do the what to say test, E and or test, that is errors and material standard test of CMM, so that your confidence and reliability of measurement will go up. That also indicates that health of the machine that is necessary to perform the maintenance. If it is not required by any company, they are not coming and asking any calibration certificate, leave that. But you want to know what is my machine capable of, what is the accuracy of my machine, what is the life of my machine. If you want to know, you can able to do this kind of test. So all machine won't give the same accuracy level. If you're buying now, after 10 years it will be giving same? No, definitely the life of the machine degrade with the time. So you have to always ensure your machine is good, capable. Even though every time you are giving, you can't able to avoid some of that wear and tear, environmental changes, okay, life and the properties of the materials being used in that particular machine, all will degrade with the time. So you have to ensure the health of the machine. You have to do the E&R test. So as I said, CMM calibration, ISO 10360 comes with the 1 to 6 subclasses. You can say subclasses: acceptance and verification test for CMM, acceptance and re-verification test for CMM ISO. It comes with 1, 2, 3, 4, 5, 6. Each and everything kind of subclasses, you can say, will come with different names. ISO this dash 1 10360 comes with the vocabularies, what all the vocabularies used in calibration for CMM, and dash 2 is explaining about CMMs used for measuring sizes, and CMMs with the axis of a rotary table as the fourth axis. So along with the XYZ, you will be having one more axis. So how to do that? And CMM used in scanning measuring mode. Dash 4 you can use. Dash 5 you can use CMM using multiple stylus probing system. Dash 6 estimation of errors in computing Gaussian associated features. So all is discussing about different CMM related thing. So in terms of E and R test, like error and materials test, material standard test. So E test is the E test is discussing about volumetric length measuring error or volumetric probe measuring error. Probe measuring error. Okay, two tests are there under E. One is volumetric length measuring error. Another one is volumetric probe measuring error. So what is meant by volumetric length measuring error? So in this error, like of what to say, length measurement error means, consider this symbol. What are all the things are being highlighted in red color? Maybe like 150, 100, 0.02, 240, like that. All like a length measuring measurements can be important. Using after doing this calibration, we are sure that what are all the measurement we are length measurements we are doing will be right. Calibrated readings only we are taking. For example, distance, we can measure the diameter or positional tolerances. If you want to say it is correct in the sense or accurate measurement in the sense, we should do first volumetric length measurement test, or this procedure we have to follow. So what is this procedure, test procedure in the sense? A set of 5 length gauges, for example, 1, 2, 3, 4, 5. These are all the gauges, stylus and probe or tip is there. Okay, stylus and tip. So 5 set, a 5 set length of gauges is measured 3 times. 3 times we have to do. For each 3 times, 5 sets are there 3 times and in 7 spectacle position. What are all the 7 spectacle position? These are all the 7 spectacle position. What are all the 7 spectacle? Along x-axis, along y-axis, along z-axis, along s partial diagonal in xy, s partial along diagonal in yz, xy and xyz. With this 7 spectacle position, 3 times with the 5 this length gauges, we have to do the measurement. So totally how many number of values will be, readings will be having? 5 into 3 into 7, 105 measurements we will be getting. So 105 measurement you have to table it, and we can able to find the statistical calculation. If you do, we can able to identify the error percentage. Okay, 100 percentage of results must be within the specification. Means for length measurement, volumetric length measurement, you will be given a certain value by the limit or tolerance by the original equipment manufacturer. So by doing this process, you can able to ensure it is coming within that given limit. So this is the test window in CMM. In CMM machine, you will be able to see in this one. So maybe I can zoom it off. So like this, different position you can able to measure. 7 into 3 into sorry 5 into 3 into 7, 105 measurements if you do, you can able to. So this is useful for distance, diameter and positional tolerance, like a length measurement error. After doing this calibration process as per ISO 10360-2, you can ensure that the readings being measured by the CMM are accurate, or with the percentage of error also you can able to say. Then volumetric probing error. So in terms of volumetric probing error, in the sense, what is the purpose of doing volumetric probing error calculation? So previously we calculated the volumetric length measurement error. This is a probing error. This is the probe for this probing error. So using that, what are all the things we can able to inspect? Volumetric probing error P. Describe the CMM error at all form inspection. In form inspection, what are the form inspection? Free form tolerance, straightness, flatness, roundness, cylindricity. Definitely we can able to measure dimensions, but also form measurement also. These form measurement also possible from the CMM. If we are telling from CMM we have measured this flatness or roundness or cylindricity with some percentage of errors. If we want to say that, first we have to do the calibration of the volumetric probe error we have to calculate. For that we have to follow. So these are all the highlighted one. The blue color one is the form errors. Okay, like parallelism or cylindricity or straightness or flatness or circularity errors kind of thing. So reference pair is measured with the 25 evenly distributed points. You have to measure 25 evenly distributed points. For example, this is the individual stylus, then this is the reference pair. From this reference pair, you have to take 25 measurements and you have to do the calculation and you can able to report it with the percentage of error. Okay, so for example here, maximum or minimum form errors from the CMM we can able to. So in detail it is given what are the position. So reference pair, from the reference pair 25 measurement you can, and you can able to get the form errors from the CMM using reference maximum, reference minimum, then sphere from that we can able to get. So how? The probing error is a positive constant, the value of which is supplied by the CMM manufacturer. Yes, the test sphere should be between 10 millimeter to 50 millimeter diameter. So in order to do this testing, you should not remember, in order to testing volumetric probing error, you should not use the sphere which is given by the original equipment manufacturer. Remember, you should not use the sphere which is coming with the CMM machine for testing the volumetric probing error. You have to use some other one. That test sphere should be between 10 millimeter to 50 millimeter. Remember, this may be the one of the candidate for MCQ. The test sphere should be between 10 millimeter to 50 millimeter diameter. Test sphere should be mounted rigidly to overcome errors due to bending of the mounting stem. Okay, so it should be properly fixed. If Because that sphere with the stem is there, if we are not mounting it properly on your table, then it may lead to bend, then measurement error will come. 25 points are measured and recorded. It is required that the points are remember, approximately evenly distributed over at least a hemisphere of the test sphere. It should cover hemisphere, at least 25, approximately evenly distributed 25 points. Okay. Their position is at the discretion of the user. It's all about us. So how they are doing? See, they are measuring like from 0, like 22.5, 22.5, 22 point, approximately. Only similarly in this, like from this hemisphere, 25 number of position they are taking. So 1 point on the pole defined by the direction of the stylus shaft of the test sphere. 4 points equally spaced 22 point below the pole, 8 points 45 degree, then 4 points, then 8 points, like that. If we do in this category or in this procedure, if we do, we will be getting 25 different readings. That readings can be compared and statistically analyzed. Based on the results, we can able to identify the form error by the CMM. We can able to estimate. Then that with that error, we can do the measurement for straightness, flatness. That is form measurement we can do, and we can compensate or we can include that error percentage calculated by the calibration procedure. Okay. So again, I am requesting you guys to go through the ISO 10360. Maybe not even though it is fully available in the website, at least go through what is there in the ISO 10360, so that at least you will be getting idea. But that details I have given here, like volume length measurement error or volumetric error. Okay. Then another one is ISO 10360-3 is talking about rotary table errors. So added with the fourth axis, as a fourth axis, XYZ is there, but fourth axis, if table is rotating, fourth axis, how to do? So they are using two sphere A and sphere B, and the radius from the center of the sphere is important, and sphere B with some height it is given comparing with the center of the sphere A. This also important in terms of measurement, and they are measuring from 0 to 780 degree 8 position, and they are reading, they are calculating. Then 8 position from again 0 to, sorry, 720 to 0 clockwise, two rotations and taking 8 reading, and anti-clockwise they are doing the rotation of the table and measuring 8 position. Then 0 to again one more 170, then 720 to 0, like that they are taking multiple reading. Then rotational error, they are calculating rotational errors, tangential error, axial errors, they can able to calculate using this ISO 10360-3. So detailed explanation is given how to do. First we have to fix sphere A and B on the RT, rotary table. So recommended height H, what they are telling for recommended height is 400 and radius is 200 millimeter. So what is the radius? The center between the table and the sphere. Okay, height is what? Sphere A to B height is 400. Then measure sphere B and set center point as a 0, 0. Means one with the height, okay, with the height H, 400 millimeter is there, na? That one you have to set as a 0. Then measure sphere A in 14 position. What are the position? 7 position from 0 to 720 degree, then 7 position from 720 to 0 degree. Then measure sphere B again in 14 position, 7 from 0 to 720, then 720 to 0. At the last position, 28 measure spheres A one more time. Okay, you have to do one more measurement. Calculate ranges of X, Y, Z for sphere A and B. So what are all the things you can able to get? So radial error, rotary table error. Radial means maximum range in X, ARB, and tangential means maximum range in Y. Axial error means the maximum range in Z, either sphere A or B. So I am not going to give the table. There is a table also there, data, some readings also there. This is not needed. Generally, you guys understand what is the procedure used for rotary table error calculation. Okay. So hereafter there is numericals. I think these numericals will be discussed in the upcoming video. So in this video we have discussed about what is calibration, why we need to do the calibration, then how to do the calibration for CMM, and what are all the potential causes of errors in terms of CMM, and also spectacle error means what, computational errors means what, and what is ISO standard for calibration, like 17025 is the testing and calibration of machines, but calibration for CMM comes under ISO 10360-2, and we have to do the calibration through National Physical Laboratory in order to ensure the quality of measurement, or in order to confident about the measurement readings or precisions and all. And E and R test we have to do, errors and material standard test we have to do in order to demonstrate the traceability along with the national standards if you want to do, then, and also increase the reliability of the measurement, and also ensure the confidence. We have to do E and R test. Under E and R test, you have a different, like a volumetric length error E, and measuring error, and volumetric probing measuring error. Volumetric length measuring error will be useful to say that what are the distance we are measuring, what are the diameter we are measuring, or what are the positions tolerance we are measuring, with what percentage of error we can, if we want to say, then we should do the volumetric length measuring error calculation. For that, we should have a 5 set of length gauges, and 3 times we have to measure under 7 spatial position. What are the 7 spatial position? These are all the 7 spatial position. With that, we can able to get 105 measurement readings. From that, we can able to estimate the volumetric length measuring error. With that error percentage, we can say what is the error percentage of distance calculation, diameter measurement, or position tolerance. Similarly, if you want to go for volumetric probing error, form measurement also possible through CMM, like straightness, flatness, roundness, cylindricity, circularity, and all. If we want to know how much error in the sense, we have to measure 25 measurement point, like randomly, but approximately we have to measure, like there is a procedure, like as I said, 22.55 like that, 4 points, 4 points, 8 points like that. You have to measure and tabulate, analyze it, and you can able to find the form error of the CMM. With that as a reference we can keep. Then if we measure the straightness, flatness, roundness, cylindricity along with the form errors of the CMM, we can give the original measurement. Similarly, rotary table error, how we can able to do in the sense using two different sphere A and B, and distance between this center of the rotary table to the sphere A or sphere B, and also height from the sphere A to B, also very very important. With that, we can able to do the multiple measurement, and we can able to identify the rotary table's radial error means in terms of x-axis, tangential error in terms of y-axis, and axial error in terms of z-axis. Okay, so with that, I am closing this particular video. So I think calibration of CMM, everything is done. Next video, I will be explaining about some numericals in this unit. Then basics about some how to do alignment errors in common machine tools. We'll discuss and close the unit number 4. So next video, I think we can wind up the unit number 4. Okay, I'm closing this particular video. We'll see you in the next video. Thank you.